Just say something. Talk about your work.
It should be.
Talk about your work. Talk, yes. John.
So what do you want?
John, just talk about your work.
So should I start off with a question of biggest fears, biggest hopes?
Yeah, I think, John, it sounds like you're going to some of the questions we've had from reporters. That's fine if you would like to do that, but we would all love to just hear from you on any thoughts that you might want to offer if you would like to do that. We may be having some trouble with the technology here.
Well, of course, the thing which I know best about is trying to fit something which does not fit into a university, into a present university or teaching framework very well, and trying to work with that in such a way that it gets modified and the institution gets modified, and so that something quite different actually in the long run is developed in the institute educational program. When I first worked in the areas for which I had been given undue honor, there were disciplines, and you didn't cross discipline boundaries. A gentleman biologist does not venture an opinion about a physics theory, for example. In the long run, new fields of science grow up at the intersection of big chunks of science, which are the pieces of knowledge now. And you have to be willing to work in those interstices in order to find out what are the limitations of the knowledge that you have and what might you do to make the subjects richer, deeper, better understood. So if I turn to this immediately to the issues of neural networks, they're often said to be neither neural in the sense that they violate huge numbers of the sacred cows of biology. And they are also things which are only approximately true in the mathematics. And yet you bring these things together and you get a subject, in some sense, you build a truth out of the partial truths. And you have to have a framework in which you can do this. A teaching framework is a very good one. One of the reasons I came to Princeton originally from Berkeley is that the faculty was actually interested in teaching. Whereas in Berkeley had reached the gargantuan size, which made that impossible. So you can develop a course which is interdisciplinary and has this life of its own if you have students who want to take the course. And that was another thing which was a very helpful part of my life here at Princeton. It was in its way much more helpful than the support which departments tended to give, which tended to be forces which said, stay where the center of gravity is. Don't go out the fringes. That's fringe stuff. The way to build a strong physics or a strong biology department is to know where the center of your field is. That's a way to build a kind of department, but it's not the only way. And if you want something which is inventive, and it may be a disaster, but maybe a triumph, you have to go out and work in the interstices some. And that's what, to me, is part of the problem of making a good curriculum, selecting a good faculty, selecting students who are interested in the kind of science which has such extensive possibilities, as well as being the possibility that you just don't find anything at all. A risk you have to take. that's all for that one at the moment. I can come back there. But I might better, from the list of questions I have in front of me, talk about the question of here's something which seems to be inordinately powerful compared to what you put it into it. How much power does it have? Does it have enough power to worry about? To worry about not just in a trivial sense, but to worry about what it does with respect to how people live, how the earth is run, because the earth is run in some sense by people. And I've watched over the course of my lifetime 2 technologies grow up which had 2 parts to them. The molecular biology revolution, which took place in the 70s and 80s, enabled all kinds of things for making new biological products. Engineered viruses, engineered neurons, engineered cell lines. These things were useful, but they're also hazardous. You remember the must have been the early 1970s. I was on a Princeton committee having to do with what should be the ground rules for doing what is now called recombinant DNA research. Because it was obvious that it had both potential for great good and potential to be militarized or accidentally to do great harm. And before you turned this behemoth out to just develop at random by faculty members, by scientists biting off particular corners and working on them, you wanted to have some idea of how you could control the system and how you could prevent disasters from occurring. And that was, of course, built on top of the nuclear physics discoveries, which enabled both the building of the atomic bomb and the generation of power plants for getting electric power from fission or fusion. And so one is accustomed to having technologies which are not singularly only good or only bad, but have capabilities in both directions. And as a physicist, I'm very unnerved by something which has no control, something which I don't understand well enough so that I can understand what are the limits to which one could drive that technology. That's the question which AI is pushing, and is pushing very much because of the neural network things which have come forth from physics and computer science and now seem absolute marvels that you don't understand how it works. Very, very unnerving. And that's why I myself, and I think Geoffrey Hinton also, would strongly advocate understanding as an essential need of a field which is going to actually develop some abilities that are beyond the abilities that you can imagine at present. Okay, enough for that one at the moment.
Professor Hopfield, thank you for. Let me summarize for the audience the questions that have been submitted that you have before you. Just so we've got a question. You've answered the first question was from the Associated Press about hopes and fears for humanity as a result of some of the discoveries. This next question is from the Washington Post, and Lizette Ortega from the Washington Post asks, some people are wondering how the work awarded today which has revolutionized computer science, fits within the field of physics? What would you say to them? How does your work fit within the field of physics?
Well, I would first ask, what defines the field of physics? If you say it's what physicists do, there's a tautology there, and you can move the whole enterprise over and still call it physics. But more fundamentally, what is physics? In my view, physics is trying to understand how systems work. The systems are made of parts. These parts interact. So when you make large systems, they get behaviors which are different from the way small systems behave, and in fact can be fundamentally new things. When you get systems which are rich enough in complexity and in size, they can have properties which you can't possibly intuit from the elementary particles you put in there. You have to say that system contains some new physics. And in trying to understand the brain, there are so many questions which you can't even make any plausible suggestion for how they work, let alone find evidence for that in biology. There's so many things of that sort that you have to say that there's going to be new physics found in understanding how the brain operates. And I think that that's true. And of course, if you look at neural nets as they are in mathematics and as they are built into computers, 99.9% of the details of biology are omitted. Everybody runs through their phone. And so it's once you get a system which is big enough and complex enough, it has properties which you, from simple arguments, explain. And at that point, a new idea comes forward. There are going to be collective properties which are not properties of the elementary units of something, but which the units produce. And condensed matter physics is an introduction to how such things can come about. My former friend Phil Anderson, dead now, another Nobel Prize. His most famous paper was, I think, called "More is Different," trying to explain how there was new physics coming out of large, complex systems. And if you want, that paper is slightly dated, but for a paper written in 1973, I believe it was, it's still very well worth reading. But so in short, I think that in biology, and in particular in neurobiology and immunology, there's new physics yet to be understood, and the problems are such that if you don't understand, if you're not motivated by physics, you just don't tackle that class of problems.
Thank you, Professor Hopfield. We have one last question. I mean, I'm combining two questions, one from the New York Times and one from National Public Radio, who asked basically the same question. They said, Dr. Hinton, your prize co-winner today, has been quite outspoken about the dangers in the usage of unregulated artificial intelligence. The question is, do you have any perspective, opinions, sentiments about AI, where it's headed, its usage as it continues to spread? What are your views?
The worry I have is not AI quite directly, but AI combined with information flow around the globe about everything you would like to know. And so you get more and more tempted to say, I know everything that there is to know. I can figure out how things work. I can predict how things go. And I think the autonomy of individual units, call them people, comes into collision with everything known by something or other, which then feed back information and change things. And so I'm worried about a world of control. The 3 decade later generalization of 1984, what 1984 was written about, was written before anybody had any ideas of what you could actually do in the way of information transmission and information in the way of controlling information interactions in such a way that you can actually control a very big system with some kind of simple algorithm, which is very successful, but you don't understand how it works. Now, at that point, if you don't understand how something works, you don't know that the collective properties you began with are actually the collective properties of the system when you all have all the interactions present, and you don't therefore know whether some spontaneous but unwanted thing is lying hidden in the works. The science fiction, what was it, Ice Nine, the premise that ice had a different structure than that which is normally expected for one of the known phases of ice. And once this was seeded, the whole crystal would spread and it would basically wipe out life as you know it by tying up water and putting it in another substance. And of course, the whole area was spurned now of polywater was actually about that many years ago. But I worry about anything which says, I'm big, I'm fast, I'm faster than you are, I'm bigger than you are, and I can also run you. Now, can you peacefully inhabit with me? I don't know. I worry.
Professor Hopfield, thank you so much for letting us spend some time with you this morning. To those of you who are listening from around the world, thank you for joining us. For those of you who are here with us today, the many of you who are here with us today, we'll have a reception upstairs following this news conference. Please join, and Professor Hopfield, we'll look forward to seeing you on your return to Princeton soon. Everyone, please join us in another welcome, a round of applause for John Hopfield today.
Thank you, John. With that, I think we're finished, and we'll look forward, as Gadi Dechter just said, welcoming you back to Princeton in the near future and celebrating with you in person. Thank you for joining us today.
Thank you for having me.